Good afternoon, everyone. Welcome to the colloquium. It's a great pleasure to have Vik Dhillon from the University of Sheffield visiting us today. He's the speaker. So Vik did his PhD at the University of Sussex, after which he followed that up with a postdoctoral position there, and then he was a staff astronomer in La Palma and also here at Cambridge, after which he moved to Sheffield in '98, and he has been there since. He's a professor of astrophysics there, and he is the recipient of numerous grants and awards, including the Jackson Quilt Medal from the Royal Astronomical Society. So Vik's expertise and primary research interests are in the field of close binary stars, and towards that, he and his team develops fast imaging cameras. So, Vik, it's a great pleasure to have you here today. Thank you.
Thank you very much, Anik. Thank you for inviting me. It's really nice to be back here. So I'll just stop my stopwatch. Right. So I'd like to speak to you about what I've been working on for the last 10 years or so, which is HiPERCAM, an instrument on the GTC. And it's primarily designed to do high time resolution astrophysics, which I'll go on to describe now. Before I do so, I'd like to say thank you to the core team who built HiPERCAM at Sheffield, Warwick, Edinburgh, UKATC Edinburgh, ESO and Durham. And particularly like to acknowledge Tom Marsh, who actually started his career here at IoA. He sadly passed away 3 years ago during an ultracam run in Chile. And Tom made a major contribution to what I'll be talking about today. So I'm going to tell you a little bit about our motivation for building HiPERCAM, quickly tell you about its design and its performance, and then show you some of the scientific highlights and future enhancements we want to make with the instrument. It'll be about 50% science, 50% instrumentation. I hope that's okay. So the motivation to build HiPERCAM was because we want to observe at high speed. So you might reasonably ask, well, why do you want to work at high speed? And firstly, we have to define what we mean by that. And when I say high speed, I'm talking about tens of seconds and below. And what that does, generalizing somewhat, what that enables you to do is study compact objects, small things in the universe. And one of the ways you can make that argument is looking at the dynamical timescales of stellar remnants, for example. That's the time it would take an object to collapse under free fall, just with no pressure resisting the free fall collapse. And if you calculate using this formula what it is for the various objects, for the sun, it's half an hour or so, white dwarfs seconds, neutrons, stars and black holes kind of millisecond. So that's pretty much the quickest that you'll get variability in any one of these three categories of object. It's the quickest that they can rotate or pulsate, or the quickest that things can orbit around them in the closest orbits in an accretion disk. So these are the kind of timescales you need to study if you want to learn more about these objects. And there's a great deal of information actually encoded in the brightness variations on these timescales of these objects. They vary in many different ways. I've just listed loads of different ways that objects can vary in the sky. And on the right, I show an example of a white dwarf being eclipsed by a red dwarf. They're completely unresolved. It's micro-arc-second spatial resolution needed to resolve them, so you can't see them separately. But you can see the very rapid eclipse of the white dwarf, ingress and then egress in the two colors, red and blue. This is less than a minute to go from the white dwarf being unblocked to the white dwarf being blocked. If you measure the speed of the star that's blocking the white dwarf, which you can from the Doppler shift from spectroscopy, then distance is speed times time, and you can work out the size of the white dwarf from the time it takes to go from there to there, which is less than a minute. And with a traditional CCD camera on a traditional telescope, that's how long it takes to read out one frame of a CCD. So that's why we needed to build high-speed cameras to be able to kind of resolve this kind of thing, because existing cameras weren't doing it. So why do we actually want to study these compact objects, these small things in the universe? A number of reasons. Firstly, obviously, white dwarfs, neutron stars and black holes are dead remnants of stars, so They provide a kind of fossil record of the previous stellar evolution that occurred to form them. They're also extreme objects in terms of gravity and pressure, magnetic field, and so they allow us to test certain fundamental physics laws. And they're also actually responsible for some of the most exotic inhabitants of our universe, like Type 1a supernovae, which are emerging white dwarfs, or emerging neutron stars are kilonovae. So they're really scientifically valuable objects, these compact objects. And I'm not just going to talk about them, I'll also talk a little bit about other small objects out there, like solar system objects, even extrasolar planets. These also benefit from high time resolution observations. So, why do we have to build our own instruments? As I started saying earlier, the problem with common user instrumentation, which is the instrumentation that the observatories build, is that they've quite rightly prioritised things like better sensitivity, better field of view, spatial resolution, wavelength range, multi-object capability, understandably, but they've really neglected high time resolution. So, as I said earlier, it takes typically a minute to read out one of the detectors the typical detector on the VLT shown here. It takes about a minute to read out till you get your data. So you can't be resolving sub-minute timescales or even second timescales with those instruments. So we had to build our own. So that's why we built HiPERCAM, and they're classed as visitor instruments, although it's gone a bit beyond that now. They're actually quasi-common user now. So what is HiPERCAM? So it stands for High Performance Camera. It was funded by an ERC advanced grant I got back in 2014, and it's also received funding from STFC to enhance it and operate it. It was built by the consortium that I've already mentioned to you, and it builds on the heritage of previous cameras that we've built, such as UltraCam and UltraSpec. UltraCam is on the VLT and NTT in Chile. UltraSpec has been in Lucia in Chile and also in Thailand. It saw first light in 2018 on the GTC, and it's got three unique features. Firstly, it uses these high-speed CCDs, which I'll explain to you in a minute. It does so simultaneously in 5 optical channels. There's 5 CCDs actually, one recording each colour, and it's now permanently mounted on the GTC, which is the largest aperture telescope in the world at the moment, and will be so until ELT comes along at the end of the decade. So therefore, HiPERCAM is the most sensitive ground-based optical camera in the world in terms of the 0 point, in terms of sensitivity you can get to in the optical. So, quick overview of the design. So on the right is the ray trace. Here's the telescope focal plane. The light is diverging after it leaves the telescope focal plane. It's collimated, so it's made parallel, and then it's split with these dichroic beam splitters, which reflect light bluewards of a cutoff and transmit light redwards. And using that, you can siphon off the various photons to 5 cameras, U, G, R, I, Z, covering the 5 Sloan bandpasses. So basically, every optical photon between 350 nanometers and a micron that enters here is recorded somewhere, more or less, in one of these 5 cameras. We don't waste any light at all. You get a single shot spectral energy distribution, SED, and we get a 3.1 arc minute field of view on the GTC with a 0.08 arc second per pixel plate scale. So this is approximately 5 times reimager, 5 times demagnifying reimager. Here are the 4 dichroic cut points. They cut in between the Sloan Digital Sky Survey filter pass bands. So you get, and because the pass bands are quite top hat-like, you get very clean separation of the photons in one pass band, go to one camera, etc. And we use these super SDS filters, which we developed with Asahi, who made the original SDS filter set, which give you much higher throughput compared to the original filter set for SDSS, which are shown by the dotted line. So we call them the super SDSS filters. So here is what the optics look like. This is almost kind of, no, not small. It's about 25 centimeters, this lens here. So it's a bit bigger than life size here. Inside this box are those 4 dichroics. Here's the collimator, the light comes in here, then it's split out into these, well, you can see 3 of them, there's another 2 at the back. You get the 5 cameras where the light comes out. So it's a sealed system against any light, stray light or against dust. For the detectors, we spent quite a lot of money. We got some custom-made detectors from E2V. They cost €1 million for the 6 science detectors we bought. We bought 1 spare and 5 main science detectors. And the reason for that was because they were optimized for high speed. I'll show you how. They have a split frame transfer format. So it's a 2000 by 2000 pixel only CCD. It's quite small really, but bigger CCDs are slower to read out. You can't clock them as fast. It's not necessarily good to go for a big CCD if you want high speed. So we chose 2000 by 2000, and this upper and lower area, as you can see in this picture, are covered in an aluminium mask. So this is the image area, the black bit, and that's the kind of storage area. And so the light is recorded in these 4 quadrants and then shifted down into its corresponding storage area and then read out from its corresponding output here. And it only takes 7 or 8 milliseconds to shift the image from there to there. So you can see an example of a frame, it's called a frame transfer design. So while you're reading out this storage area, which can take up to a second in these detectors, you can build up the exposure, the next exposure. There's no shutter, a mechanical shutter going across. It's an electronic shutter. This shift takes 7 milliseconds, so that's far quicker than a mechanical shutter could actually block the light. And it means that you've got a 7 millisecond gap between each exposure. The exposure can be as long as you like, but you're not waiting a minute for it to read out. You're only waiting 7 or 8 milliseconds to read out. And you can do faster than that if you want. We can go actually up to 1,000 hertz frame rate, so 1 millisecond frame rates, exposure times. Various other things about the CCDs that are really optimized for both high speed work and sensitivity. We really did not want to waste any photons. Here, just very quickly, here's how they're packaged. We didn't want to make a monster instrument because we knew we were going to have to be quite versatile in where we mount, so because we're a visitor instrument. So we tried to make everything as compact as possible, and that included cooling our detectors with Peltier cooling, very deep cooling though, -90, we can go to -100 degrees centigrade with Peltier cooling, not with traditional liquid nitrogen or closed cycle coolers. And this enables us to electrically cool the detector with no cryogens or anything like that. These generate a lot of heat. They take a lot of heat out of the detector to cool it down to -90. That heat needs to be taken away with a water circuit, which goes through this heat sink here. Water's at 5 degrees. And the advantages are that this is extremely convenient. You'd be able to turn the cooling on and off with a switch. You have no liquid nitrogen or anything. Much lower cost. There's no vibrations. Much lower mass. They weigh 7 kilos each, and they're kind of this big, the detectors. So we can make a much more compact instrument. Everything's cheaper and easier. So here they are, being ready to ship. We color-coded them according to the filter they were looking at. And here is integration. This was at UKATC in Edinburgh. You can see here on the hull I showed you earlier, now with the 5 cameras bolted on. And unfortunately with 5 cameras, you've got 5 sets of cooling circuits and controller cables and all of that stuff. So it gets quite busy. We had to mount that on a telescope. We obviously couldn't mount it like that. So we built this optomechanical chassis, which could mount on the telescope and have all that previous stuff inside it. This is what it looks before. And this is what it looks like afterwards with all that stuff then in it, mounted on the telescope now. And then we had first light. This, of course, isn't really first light. It was a horrible out-of-focus star was first light. But yeah, this was on the first night, at least. We got, everything worked well in 2018, on time and on budget. Right, so performance-wise, we've been really pleased. So here are U, G, R, I, Z. We get simultaneously these 5 images, 3.1 arc minutes across the diagonal. We had no ghosting, which we were really pleased about because we were using dichroics, but it's an collimated beam, so you don't expect ghosting, and we didn't see any. Very uniform plate scale. By that I mean that the star occurring on this pixel here, XY, has the same XY there, and there. That's very important because we need to put small windows over those stars and only read out just the pixels around those stars if we want to go really fast. So the star has to occur on the same pixels in all the detectors, so we can avoid some horrible asynchronous controller stuff. There's no vignetting at all, and we get really good point spread functions. This GTC is a fantastic telescope. It can deliver 0.3 arc second images. I've seen that quite regularly, and HiPERCAM can exploit that. It doesn't add any additional blurring due to the optics. We can get the image that the GTC is providing. We can fully exploit. 0 point wise, it's really sensitive. So here are if you're not aware what 0 points are, it's the magnitude of a star that gives you 1 electron per second above the atmosphere. And it's a sign of the sensitivity of an instrument. And these are in the 28s, 29s, which is fantastic. I mean, as they would be, it's the biggest telescope in the world. It should be sensitive. But in comparison, here is the previous, before HiPERCAM came along, OSIRIS is the main common user instrument on GTC for imaging, and it beats the 0 points by, in the blue, well over a magnitude. And that's because you'd think we'd lose a lot of light because we've got dichroics and splitting the light up. Surely there's photon loss, which there is, although the dichroics are surprisingly efficient, actually, a high 90% in efficiency. But what we were able to do was OSIRIS, and any broadband imager, has to be able to record photons from U to Z, from 300 nanometers to 1 micron, across the whole spectrum. But our CCDs don't need to do that. Our U-band CCD is optimized just to record U-band photons. It's got a coating which is super efficient in U, terrible in the red, but that doesn't matter. It's only recording U photons, so we can recover that efficiency that we might lose slightly from the dichroics and actually beat the common user instrument quite substantially. So the bottom line is we can detect 23rd magnitude objects in 1 second and 28th in about an hour. So this was a really whole new ball game as far as variable star research is concerned, the depths that we could go to in these times. And talking about times, this is critical for HiPERCAM. Because we're going so fast, we have to have very accurate time stamping of when the actual exposure was taken. So we have a GPS system that we use to nothing to do with position, it's time stamping each frame. We've tested this in various ways, and we think it's accurate to a few tens of microseconds in absolute timing. You can tell the middle time of the exposure to within a few tens of microseconds, which is really important when we want to cross-correlate our data with an X-ray satellite or a radio telescope. We need to be confident in our timing. Right, so how am I going here? Okay, good. So I'd like to tell you now a bit about the science we've done. That's everything about the instrument so far. So first I'll try and give you a bit of a broad brush outline of what we've done. Bearing in mind that we built this camera, my research interest, Tom's research interest and collaborators, it was in the field of white dwarf binaries, neutron star, black hole binaries. That's what we're really interested in. But we realized that the instrument would be useful for other things. And as it turns out, it's been used for a whole host of stuff. So yes, we've observed lots of binaries, black holes, white dwarfs and neutron stars, and actually some isolated systems of those as well. But we've also observed brown dwarfs, exoplanets and exoasteroids. We observed quite a few different types of solar system bodies, AGN, fast radio bursts, gamma ray bursts, supernovae, fast X-ray transients, ultra diffuse galaxies, and even some ultra deep fields. So people are using not just the high speed capability of HiPERCAM here, they're using the fact it's on the GTC, so it's incredibly sensitive, and you get the 5 colors simultaneously. They don't actually care about the high speed, but they do care about the sensitivity and the 5 colors. So there's been a kind of combination of uses. And people have been far more, sorry, I should say, we've opened up HiPERCAM for free to use for whoever wants to use it. You're welcome to use it. And people have been far more imaginative than we have in actually thinking up clever ways of using the instrument. We've actually done some things like lucky imaging, photometric redshifts, occultations, transmission spectroscopy of exoplanets, low surface brightness imaging, things which we didn't really foresee there'd be a use for. We've actually done quite a lot of that kind of work. I'll show you examples. Before I do so, I'll just summarize HiPERCAM in numbers. This is all courtesy of Romano Corradi, the director of GTC. They monitor these kind of numbers for all of their instruments to see how they're performing and cull them or keep them depending on how the numbers go. So we've now been allocated nearly 1,900 hours of telescope time. We've actually operated for 11 different semesters now on 2 different foci on the GTC, as I'll show you. So we're quite well established. Approximately 70 refereed papers so far, 9 of them in high impact journals. And it's now become the most productive GTC instrument in terms of the number of papers per hour and a fraction of which are high impact. This is all according to the GTC director, so he tells me all this. And it's now behind only OSIRIS, which is their main common user spectrograph and imager in terms of the total demand for time on the GTC. Right, so so that's just the kind of director. It's been well received, HiPERCAM, and they're supporting it. They like it. The community seem to like it. So we're staying on the telescope, hopefully. So now I'm going to give you a kind of summary of some of the highlights that of the results we've obtained with HiPERCAM. The first few are about white dwarf binaries, and we had two results really early on, soon after first light, and it was a real great morale booster for the team, actually. We'd been working so hard for so many years to get it onto the telescope. It was really nice to have a couple of nice results immediately. This was one of them. It's a white dwarf. This is obviously an artist's impression. We have a white dwarf in orbit with a red dwarf, a 3-hour orbit roughly, and there's an eclipse once per 3 hours. You can see that here in the 5 wave bands, U, G, R, I, Z. There's a white dwarf eclipse. And in fact, you can't see it on the scale of these plots, but there's a secondary eclipse here when the white dwarf is behind the red dwarf, which is only a 1% dip. Remember, that's an Earth-sized object, the white dwarf, so we're seeing it going behind the white dwarf. Sorry, going in front of, sorry, let me start again. The primary eclipse is when the red dwarf covers the white dwarf, so that's a deep one. The secondary eclipse is when the white dwarf transits the face of the red dwarf, apologies, and that's a 1% dip only, and we were detecting it in this 19th mag object. The reason this was an exciting result, I should say, is because it was the first eclipsing binary that was found to have a cool subdwarf. This is a low metallicity dwarf star. And the key thing is it's an eclipsing system, so that means we can measure the inclination of the orbit, and from the radial velocities from spectroscopy we can determine the masses and the radii of both objects to really exquisite detail, like 1 or 2% accuracy on the masses and radii. And that enabled us to test whether cool subdwarfs are actually smaller in size than a normal metallicity dwarf star, and we found it was, and it was the first time you could really test. And the reason for that is lower metallicity, you have a lower opacity in the atmosphere, and you expect the radius of the star to be smaller than a normal metallicity star, and we verified that was the case. So that was a nice result. Another white dwarf result we had very early on, another morale booster for the team, was this one, where we have 2 white dwarfs in orbit, and one of them was a pulsating white dwarf. And because they eclipse, and we can measure the radial velocity curves of both of them as well, again, we can measure the masses and radii to really lovely precision, a few percent. And this is now a benchmark object because we can do astroseismology on the pulsating white dwarf and test whether the masses and radii are compatible with the actual measured masses and radii that we get from the dynamical and eclipse study. So it's kind of a test of astroseismological models of white dwarfs. Then we also found this new class of star, the white dwarf pulsar. This one is called AR-SCO. We found 2 more now. There's 3 we've definitely known as a few more candidates as well. This is an amazing object, as you can see the light curve. You've got U, G, R, I, Z with HiPERCAM. This is the about 2 hours or so of data. And that pulsing you can see is the white dwarf pulsing every 2 minutes, giving us this strong increase in flux in those wavelengths. And the reason it's a white dwarf pulsar is because it's powered by there's no accretion going on. It's powered by the spin down of the white dwarf, just like a normal radio pulsar is powered by the spin down of the neutron star. And it also emits across all wavelengths, radio all the way to X-ray, just like normal pulsars, neutron star pulsars do. Hence, these became called white dwarf pulsars. Quite a lot of theories have been proposed for the actual origin of the emission. It's definitely synchrotron. Exactly where it's coming from is unclear. Actually, there's some threading of the field between the white dwarf and the secondary star going on, because we do see a beat period, which is the orbital period, beat of the orbital period and the spin of the white dwarf in the signal here. So there's something going on with emission from the white dwarf and the red star. So one of the challenges here theoretically is understanding how can such an object spun up to these 2 minute periods. It's got a strong magnetic field. So if you have a strong magnetic field and a highly spinning white dwarf, any matter that would be needed to accrete onto it to spin it up would be just flung off by the fast rotation of the white dwarf. So trying to understand how such a system can be arrived at is quite a theoretical challenge. Finally, on the last bit of results before I move on away from bright white dwarf binaries, is we've realised that we can measure the times of these eclipses really accurately, and we can use these white dwarf binaries as a direct measure of the acceleration of stars in the galactic potential. And if you can do that, you can actually estimate what the Oort limit is, which is the kind of mid-plane mass density near us in the galaxy. And if you know the Oort limit and you know the baryonic content, you could subtract one from the other and get the local dark matter density, if you can measure the accelerations of stars. Now, this is tough. People have tried it with radio pulsar timing, and also, I don't think it's been done, but it's been proposed, extremely high precision radio velocity measurements as well of stars could, in principle, measure the acceleration, the change in the velocity of the star with time. So we're investigating whether we can actually use the eclipse time variations of double white dwarf binaries as a third route to do this. So this work is being led by Sukanya Chakrabarty in Huntsville. Now, the accelerations are tiny. We're talking tens of centimeters per second per decade. That's in terms of measuring. But this turns out to be 0.1 seconds eclipse time variation of a double white dwarf binary over a decade. And we can measure that. Here's an example of one of our double white dwarf binary measurements with HiPERCAM. And we can measure this to a few tens of milliseconds. So if we can do this over a decade, or maybe less, because we actually can measure it really high precision, we can maybe do this. So we have been monitoring this particular object. It's called CSS 41177. It's a double white dwarf, 2.8 hour period. So there's no accretion going on. They're really very widely separated for white dwarf binary. And we have actually been monitoring it with our other camera in Chile, UltraCam, for more than a decade. In the last few years, we've been doing it with HiPERCAM as well, where we're getting much more high signal to noise light curves and better, lower error on the eclipse time. And we think we might be there. We're now competitive with the pulsar, so Sukanya tells me. And we're monitoring 2 or 3 others of these white dwarf binaries. So I think we're hopefully going to report on this in the next few months, that we have established a new kind of timing standard in the sky that we can use. And the nice thing about the white dwarfs is it's a check on the pulsar results, but it's also a different distribution around the galactic midplane than the pulsars have. So we can test for the existence of dark matter subhalos in principle, due to the different distributions of these clocks that we're using in the sky. Right, talking a bit more about timing. JWST, during their science verification stage, wanted to know how accurate their clocks were on board, because a lot of people do want to do time-resolved work with JWST as well. So we helped them with this. The pre-flight expectation was that the timestamps per frame of JWST would have an error of about 0.5 seconds about when the middle of the exposure was, which is not very good if you want to correlate with another facility, for example, or to establish some kind of ephemeris. So we've been monitoring regularly one of these double white dwarf binaries, have a very accurate ephemeris for it. But we also, as well as they could have just used that, but we also did a simultaneous observation with HiPERCAM and JWST. And there's one like over, there's ours. And we verified, that actually JWST is much better than specified. It's good to kind of 100 millisecond level timing. So that was an important piece of information going forwards for future scientific use of JWST. Right, that's white dwarfs. So now moving on to neutron star binaries. The type we've been really interested in are the millisecond pulsar binaries, and there's a movie of one here looking down from the top of the orbital plane. You've got a rapidly rotating neutron star. We're talking milliseconds spin periods here. These are the fastest rotating neutron stars known. And in orbit with a low mass companion, which is being ablated by the particle and radiation field from the neutron star. And these are called a black widow pulsar, because it kind of eats the companion, like the spider. And the reason we're interested in these is these neutron stars have been spun up to millisecond periods, and that must have taken some accretion to spin them up that fast. And therefore, these neutron stars are probably the most massive neutron stars known. Most radio pulsars, isolated ones, are 1.4 solar masses. Pretty much all of them are, just over the Chandrasekhar limit. But these ones, they look like they're 2.1 even solar masses. And what we're searching for here is where do black holes start and neutron stars finish? What's the maximum mass of the neutron star? If you're going to find the maximum mass neutron star, if you can find one that's 2.5 solar masses, that really constrains the equation of state of the neutron degenerate material. So we've been targeting these systems, measuring the masses of as many of these neutron stars as we can find to find out where does a black hole neutron star dividing line occur. And HiPERCAM comes in because we can't see the neutron star on the optical at all, but you can see the companion star, and it's irradiated heavily on the inner surface, and it gives you this characteristic irradiation profiled light curve. This is one orbit, 2 orbits, 3 orbits, where you see the day side of the irradiated companion come into this line of sight, and then it comes around the back and you look at the night side and then the day side, etc. And we can model these light curves and determine the inclination of the binary, which combined with spectroscopy and information from radio as well, gives us precise mass measurements for the components. So we've been doing a lot of this with HiPERCAM. And the reason is because we can probe to these incredibly faint magnitudes. We're doing short exposures here, and we're getting to 26th mag, easily detecting it, 27th mag even down here in the bottom. So it's really opened up a whole new area for us with the sensitivity of thanks to being on the GTC. And this is the previous kind of best light curves for comparison of this object with HST and this object with Keck and Gemini. Remember, these telescopes have only got single band images. They have to take one filter, wait a minute for it to read out, move the filter to the next one, take another one, build that up over time. We can get all those things simultaneously with no dead time. So hence the difference in quality between the light curves, even though the apertures of the telescopes are actually quite similar. Okay, moving on now to black hole binaries. We've done quite a lot of these. The main aim with these things is try and work out where the optical emission is coming from and use it to constrain the emission regions in the binary. Where are the optical photons produced, the X-rays produced, and what can we infer about the accreting structures close into the event horizon around the black hole, which is right at the center of the accretion disk here. So we do a lot of simultaneous work with X-ray satellites. So here's I think that was NICER, this one. And these are the 5 HiPERCAM light curves. This is seconds here on the x-axis. There's a very small portion of light curve. And then you cross-correlate the light curves, X-ray to optical. Before I show you that, zooming in, these flares that you're seeing due to the accretion processes right in the inner part of the disk here are resolved, and they're really short. These flares are going up and down in a fraction of a second. They're quite red, pointing to it to be synchrotron emission. Because they're so rapid, they also must be coming from a small region, of course. And if you cross-correlate between X-rays and optical, we find lags of 1/10 of a second, roughly. And we've seen a similar thing in 2 others, at least, of these systems. It's pretty common, this 1/10 of a second lag. The X-rays go up, and then a 1/10 of a second later, the optical goes up. And not only that, the blue goes up first, then a little bit later the green, then the red, then further in the red, etc., as you're going redder. And so the kind of picture that's been building up is we're probing this inner region of the jet, this kind of launch region of the jet here. X-rays are coming from very close to the event horizon. And then as you move out, you're getting the blue, green, red light. And this kind of 0.1 second light travel time. So we're talking kind of 100 to 1,000 Schwarzschild radii above the black hole. So we're effectively using the time resolution here as a kind of proxy for the spatial resolution, kind of working out what's going on right down there around the black hole. We've observed, so I'm moving away from stars a bit now. Exoasteroids, we've observed a few of these. These are there's a dozen or so, maybe a bit more known, of these white dwarfs which are surrounded by debris disks, which are clearly the remnants of planets or asteroids that were originally orbiting around the white dwarf. They strayed inside the Roche limit, got tidally disrupted, spread out into a kind of disk. which artist's impression shown here. And you see these transits occurring. In this particular object, the typical orbital period of the objects in the disk is about 4 hours, 4.5 hours. And you've got, if you add it up all the mass, it looks like it was a series, the asteroid series type mass of object that was disrupted to create the kind of things we see. And we see these dips from the larger objects in the debris disk recurring every 4.5 hours, but then they evolve. If you observe them over enough cycles, they change, and you can see the debris disk actually evolving through collisions and other processes. And from the depths of the various transits, as a function of wavelength, we can infer things about the particle sizes as well in the debris disk. So we've done quite a few of those. Okay, here's another example. Craig will really like this, wherever Craig is, because this is lucky imaging. And I'm sure Craig would have given them the same advice when they approached me as I did. They said, we want to do lucky imaging with HiPERCAM. And I said, forget it, you can't do lucky imaging on a 10-meter telescope. You've got too many of these R0 Fried length patches over a 10.4 meter aperture to get any chance of that being anything other than incredibly wasteful of telescope time. But they went ahead and did it, and it worked. I was amazed. They imaged Neptune. The aim of this project of theirs was their zonal. They want to measure the wind rate as a function of latitude, the zonal winds. And there's also this dark vortex, which isn't shown actually here. There was a U-band image as well, which showed this dark feature, which is unexplained. And they were monitoring it with HST, but they needed to carry on monitoring it from the ground, and they were doing it with this. So these were, I think, 30 millisecond exposures. And you chuck away the ones where the seeing's poor, then shift and add the remaining ones to get a much higher resolution image than you'd expect from seeing. So staying in the solar system, this was a really exciting result. It was really exciting to observe it at the time. There was a prediction of Quaoar, which is one of these dwarf planets that are outside the orbit of Pluto. They're Pluto-sized objects. They're one of the reasons Pluto got demoted as a planet, because there's other objects just as big out there. And this one was predicted to occult a background star, and the shadow of the occultation was going to pass over the Canary Islands observatories. So a campaign was led by a Spanish group, and GTC was involved in the observations with HiPERCAM, but they had other telescopes and satellites actually also monitoring it. And as I say, it was very exciting because you saw this. This is a Palma finding chart. So this is the positions of objects 50 years ago. So Quaoar isn't in here, but when we were observing it, Quaoar was here, and it moved across, and it occulted this star here, and then carried on in its motion across. And bang on the second that they predicted it would occur, we saw the dip in the light curve. Here's the light curve in 4 of the bands with HiPERCAM, and this background star just almost disappeared. It took this is of about a minute it took for the occultation to start and then end. And the original aim with this is, if you do this, and you do this at a number of different locations on the Earth's surface, you can measure the size of Quaoar, which wasn't known. You can measure the radius of the object, which is really important. And also, if you look carefully at the shape of the ingress and the egress of the occultation, you can infer the presence of an atmosphere and put limits on the pressure of the atmosphere, because the thicker the atmosphere you have, the more rounded that ingress feature would be. And you see it's absolutely razor sharp here. There's almost no evidence of an atmosphere at all. We've done Pluto, where you do see a little bit of a curvature. So that was really nice. We measured the size of the object. But what was really unexpected, I was observing this particular one. It's so very exciting, and great. That was a nice observation. But then a few months later, they contacted us, the lead authors, because they'd checked and they'd found a dip before and after, about 2 or 3 minutes before and 2 or 3 minutes after the main event, which we hadn't noticed at all at the time of observing. And it's consistent with the occultation of a ring around Quaoar. And actually, it's a really unique ring, because it. And this is the HiPERCAM data, but it was actually confirmed also by 1 or 2 of the satellites that also observed it. Cheops was one. This ring, unlike any of the 6 known in the solar system, this is the 7th. The other 6 rings known in the solar system are all inside the Roche limit. But this one is way outside, 2-3 times outside the Roche limit. And you wouldn't expect to see a ring here. Outside the Roche limit, if there's a ring of debris, you'd expect it to quickly coagulate into a moonlet in timescales of thousands of years, maybe. So what's the chances of us having observed Quaoar just in that 1,000-year epoch when it happened to have a ring there? It's quite low, given the lifetime of the object. More likely it's somehow surviving out there as a ring rather than coagulating into a moonlet. And the idea here is that actually the particles are actually quite hard. They're more like hailstones and snowflakes. So the collisions between them are quite elastic, and that resists the moonlet coagulating. That's the theory. So that to explain this one. Right, moving on to larger scales now, extragalactic. We've monitored a few AGN. So here we have the HiPERCAM light curves over a few hours of this particular AGN, NGC 4395, in 5 wave bands, again, UGRIZ. And then if you plot the lag between the X-rays and the optical, you see the HiPERCAM points are in red here. I think these are from XOMM optical monitor in the blue. You can see that the lags level off. And what this means is, well, the interpretation of this is X-rays are emitted from close to the supermassive black hole, propagate outwards and heat the disk, the inner parts first, and then as you move out, obviously the outer parts, the inner parts radiate predominantly blue, they're hotter, the outer parts predominantly red, so they're cooler, so you'd expect the lag to increase with wavelength, just like this. But the fact that it levels off like this suggests that you've come to the edge of the disk, and you've got a measurement of the actual disk radius and proof that it truncates, which obviously it must do at some point. But you can actually estimate the radius of the disk. This is in Schwarzschild radius, the radius of the disk around this particular AGN. And so it's a really powerful way of getting the parameters of the AGN disk. I think this is my last example scientifically. Surface brightness, low surface brightness galaxies. We've done quite a few of these. Here they don't care at all about the high time resolution. All they care about is the 5 colours and the sensitivity of HiPERCAM on the GTC. Yeah, they're studying these very low surface brightness. I'm talking here 31 magnitudes per square arc second in the weird units the community there use, which is 10 by 10 arc second boxes, not 1 by 1 second arc second boxes. But this is Nube, probably the most extreme one they've studied. It's the same mass as the SMC. So remember, that's 1% of the mass of the Milky Way or something. But it's got a third of the size of the Milky Way. So it's almost as big as the Milky Way, but a few percent of the mass. So that's a really strange situation. Now, one thing you might say immediately is there's some kind of tidal stripping, but they've carefully analysed this and others, and they see no evidence of any kind of tidal effects, any streams or tails or anything like that, so signify that might have happened. And what they like about using the HiPERCAM is the 5 colours. They can measure the spectral energy distribution of the galaxy, and then therefore they determine the age, the metallicity, and the properties of the stellar populations in them. And as I understand it, this is not my scientific area, this is a challenge for lambda CDM models to produce in the cosmological simulations, galaxies with these kind of properties. Right, so that's scientific highlights. Very quickly then, I'm going to go through the enhancements in my last few minutes. So we were actually mounted for 3 years on this focus, folded CAS-E, it's called, on the GTC. You can see HiPERCAM there. But then this disappeared, this visitor focus. And we used to mount on for a few weeks, then take everything off, and then put it back on again. It was a huge amount of work, 2 or 3 days each time, putting it all on, taking it all off. And bad for the instrument, bad for us. It was really difficult. And of course, COVID was like a year and a half at least of this as well. So we didn't get that much time on the telescope in that period. And then this focus no longer became available because they had a big common user instrument called MIRADAS, a multi-object infrared spectrograph going on there. So they said we could use this focus here, which at the time was just a bare hole in the side of the telescope. There's no rotator, which you need to correct for the image rotation. There was no services, water, Ethernet, anything, electricity, nothing. And it's quite small. You can see this is the Megara, another instrument. If we put a rotator that big here, it wouldn't fit. It'd clash with that one. So the challenge was the small space envelope and the lack of any services. We had to create a new focus on the telescope if we wanted to remount HiPERCAM. So fortunately, STFC gave us some money to do this. We built and we had to design it first, verify it would actually fit, which it does by a matter of millimeters, it fits. And this is the very first time we rotated it actually on the sky, on the telescope. And you won't see it in this movie, but there's some jockey wheels up here and they come around and they just miss this rotator here with the other instrument by a few millimeters. We just fit in the space envelope. But it gave us finally a permanent focus. We know no one else could use this focus. No other instrument would be able to fit on this. We're quite small, really, our instrument. And you see our electronics also had to be really long and thin to fit in the space envelope, that cabinet there. And this significantly suddenly increased the amount of observing time we could get, enabled us to study transients for the first time. Previously, we had to be lucky a transient went off when we happened to be mounted, which wasn't that often. Now we're permanently powered up. All they have to do is move the tertiary mirror of the telescope and they, within a few minutes, can start taking data with HiPERCAM if they want. So we can do much more in the field of transients, and we can also do much easier to simultaneously observe with other facilities like X-ray satellites or radio telescopes. So it saw first light on this new permanent focus in 2023, and it's been used continuously since then. We operate it under this agreement that the HiPERCAM team have signed with GTC. Anyone can use the instrument. It's freely available for use by anyone in the community. We get, in return for supporting it and providing it and maintaining it, we get 1 hour per 6 hours awarded to external teams. We get 1 hour of guaranteed time. Right, so I haven't got time. I'm going to skip over this section here. Sorry, this is describing a comparison star pick-off system that we've built, which is very differential photometry aficionados only would really care about this. So I'm going to skip over this. And I'll also skip over this as about a diffuser, which you use for exoplanet observations to give us stable PSFs, to give you really good light curves of bright objects. I'll skip over that. I want to talk about the final thing, the final enhancement I've been working on at the moment. It's called HiPERPOL. And it's going to be adding a polarimetry module to HiPERCAM. So just to remind you, there's 5 things you can measure from light: the flux, the number of photons, the direction they come from, the wavelength, their time of arrival, and their polarization. There's 5 fundamental things you can measure from light. And polarization is sometimes overlooked, really, as one of the properties that is not often measured. And the polarization of the light wave, it refers to the orientation of the electric field component of the electromagnetic wave. And unpolarized light has completely random orientations of the plane. Polarized light has some partially polarized light has some overabundance of one particular orientation. So then you have linear polarized light in that case. If that plane of polarization rotates with time, you have circular. And if it rotates with time and the amplitude changes, you have elliptical. So that's quick background of polarization. So, and it offers a unique view of the universe. It's sensitive to 2 things: scattered light, so that's light reflected off solid or even liquid bodies, or scattered off gas and dust. And it also is sensitive to the presence of magnetic fields. It can tell you if magnetic fields are present in an object and helps you determine the properties of the magnetic fields through, for example, the cyclotron or synchrotron signatures. So if we had such a capability, we'd really be able to address a broad range of science, from polarimetry of these interstellar comets and asteroids that have been visiting us recently. You can infer details about the surface properties of the objects you can't get through other means. Looking at the mergers of neutron stars like kilonovae, there are predictions about the polarization signal that you'd get from kilonovae that would confirm that you have a disk of R processing, a disk of material that's in which the R process is occurring, making the heavy elements of the universe. And we'd be able to detect that disk through the asymmetry that it would impart on the polarized signal through the scattering in the kilonova. It's equivalent to resolving, it's like 10 minus 16 arc seconds effectively. You can get 10 minus 16 arc seconds spatial information by looking for asymmetries in polarization. So that's kind of amoeba in the Oort cloud type resolution. It's really amazing what you can do in principle with polarization. And finally, also big objects like AGN are polarized. the light from the AGN is scattered by dust, and that gives you polarized light, which could be confused with stellar populations. So disentangling between the two is important to understand the importance of outflows and the evolution of these galaxies. So it's a really important technique. And there aren't that many on big telescopes. Here is what we propose to build, HiPERPOL on GTC. And here are the others currently available, the best of which scientifically, definitely in terms of the results, is VLT4s. But that's only on an 8 meter, it's a factor of 1.6 fewer photons than GTC. It can only do 1 filter at a time, we do 5. It can't do high speed, but it is permanently available, which is good for transients. If you want permanent availability, you don't want to put your instrument on and off every time you want to use it. So it's very competitive as far as comparison with other telescopes. If you look in terms of raw number of photons, remember polarimetry is a really photon-starved process. We collect 10 times more photons than the nearest rivals if we had HiPERPOL. So it's very sensitive. Stop going. Also, none of the next generation of telescopes have got any kind of polarization capability. So if we built something like this for GTC, it would be the leading polarimeter for many years to come. So that's the motivation to want to build HiPERPOL. It'd be a classic dual beam polarimeter. So it would have a quarter wave plate or half wave plate for the modulator and a Wollaston prism for the analyzer. And it would be located in here. Be located in this part of the instrument here. So we wouldn't build the new instrument. We'd be injecting light from this module into the existing instrument. And here it is. You can see here's the polarimeter itself. It slides in and out in these rails. So when you don't want to do polarimetry, you slide it out. You can do remotely. And when you do want to do it, you slide it in. And then on the actual unit itself, it's got a half wave plate, quarter wave plate. There's a Wollaston down here and polarizing filters for calibration. And it, again, opens a really new territory in terms of sensitivity. This shows you the exposure time required to get to this limiting magnitude in polarimetry, where the dash curves are a 10% polarized object, and the solid curves are 1% polarized. So we can get to 25th magnitude in 1 hour, or rather, we can detect 10% polarization in an object as faint as 25th mag in 1 hour. That's really new territory in terms of sensitivity. And we can even do 20th mag in 1 second. So there's strong motivation to do this because it's so sensitive. So I've applied for another ERC advanced grant for this. I've got the interview in a week, so fingers crossed it goes well. Hopefully it does and we can build this. It'll take 2 years to build, we believe. So, summary, sorry, I'm slightly long here. HiPERCAM is a proven instrument now. It's permanently mounted on this large telescope. We've done a really wide range of science with it. It's available for use by anyone in the community. It's not a private instrument. Future plan, our main one, is the provision of polarimetry. And it really does give astronomers in the community a unique capability, particularly in the field of time domain science now. I think it's where it really will be used a lot in the next few years, because as we start finding exciting new transits of Rubin, there's a 50% sky overlap between Rubin and GTC. So plenty of Rubin targets will be visible for us. That's it. If you yeah, sorry.
Thank you, Vik.
Pleasure.
Yeah, do we have questions? Hey.
Thanks for the nice talk. I'm really curious about the white dwarf pulsar object in particular. So, is there any size constraints on the emitting region? Is there any VLBI observations? And do you have any constraints on potential thermal emission?
Potential?
Thermal emission? Is there any thermal emission at all? Is it purely?
Yeah, no, there is. There was an underlying variation there, which we believe is thermal. But the pulses are synchrotron from the spectrum, and they're highly polarized. I didn't show the polarization, but they're 20, 30, 40% polarized linearly. So so that's what really nailed it as the process, actually. VLBI, I don't think so. But you're talking micro arc seconds. Can VLBI go to micro? No. So, yeah.
Thanks for the great talk. I certainly hope your interview goes well because
Thank you.
polarization would be amazing. Can you say a bit about when, if everything goes to plan, like when would this be available? And then kind of as a corollary to that, a lot of the observations you were talking about seem to be sort of one-off types of things, but is there like a large program mode, or is that something you might envision?
Yeah. So timescales, if I'm lucky enough to get the grant, it would take 2 to 2.5 years to get the instrument on the hyperpole onto the telescope. So 2028, end of 2028-ish. So it's not too long actually, because the 5-year grant was actually then exploitation for the last part of the grant. And then large program-wise, yeah, we use our guarantee time and we apply for time for regularly monitoring a whole load of white dwarf binaries, which is really our core thing. So that's the only thing I say we do that's really long-term planned, and we've got regular observations. We're monitoring lots of these double white dwarf binaries, but also white dwarf, M dwarf systems. So certainly nothing in the way of monitoring. I know you're maybe coming from the X-ray binary point of view, nothing long-term on that. It has indeed been, 1820 and V404 SIG and the usual suspects. So
the reason I was sort of asking is, there's a long history now of co-monitoring with really, cheap optical permalimimeters, like 1 meter ones, with high energy facilities. And I see that there's a polarization flip often coming together with, high energy emission flaring. This kind of multi-messenger era coming up now with CTA and then also like neutrino experiments.
Yeah,
it might be really interesting.
That's that. No, very nice to talk to you about that afterwards. Yeah, very interesting. Yeah, that'd be good. I didn't have that in my science case actually for the for the grant. Yeah, yeah.
Let's take 2 more questions. So maybe you first here. Mm-hmm. Go ahead.
You were talking about sort of multi-wavelength emission from jets and how that seems to decrease in wavelength away from black holes. Is that primarily an effect due to the magnetic field decreasing in flux density away from the black hole? And if so, would polarimetry in the visual allow you to better sort of probe the outer regions of those jets?
Yes, I think that your first thing, yes. The second thing is polarimetry. Certainly it's synchrotron, so you would expect linear from it. Whether that would let's go further out though, I don't know. I don't think so. Because we're using the time delay, so we'd have to do really fast polarimetry. I glossed over the polarimeter cannot go at milliseconds because you've got to rotate the wave plate 4 positions to actually get a single polarization measurement. So we'd struggle to go quicker than half a second or something. So to get time lags in polarimetry is really challenging. That short 0.1 second time lags. It's very difficult for us, unfortunately. Yeah.
Thank you.
Yeah. Thank you.
One last question.
Hi.
Could it be that there are things like fast radio bursts which put that amount of energy in the optical band in less than a millisecond? And you gave an example of a 25th magnitude objects which have to observe a long time. But if you have something which is very bright for a very short time, what are the constraints on observing it?
Yeah, you've touched on something I've spent, I don't know how many nights in the last couple of years observing fast radio bursts simultaneously. HiPERCAM with Effelsberg, which is the largest dish, single dish, 100-meter dish in Germany. And so we've simultaneously for hours and hours monitored FRBs, taking, as you say, very fast images in the optical to catch assuming they're millisecond duration in the optical as well. You don't want to take a long exposure, you could just lose the the flux in the background. So, and unfortunately, we've monitored 5 or 6 now and simultaneously detected radio bursts and simultaneously been observing the optical when a radio has gone off, burst has gone off, that's actually rare in itself because we've wasted countless hours where the radio's just detected nothing. We've just collected nothing but noise with HiPERCAM. It's very frustrating. But anyway, we have had some radio bursts go off and then we go, oh, great, it's gone off. Let's check the frame. Did we see anything get bright? And even in the brightest the nearest FRBs in M81, it's a repeater in a globular cluster around M81, 3.6 megaparsecs away. It's by far the closest FRB. You'd think that's the one. If you're going to see something in the optical, that'd be the one you'd see, and we didn't see anything. So that was really disappointing. So they don't seem to be emitting anything at the 20, I don't know what the limit is, we got to 24, 25 mag in the optical. So we could put a limit on it, but we can't, unfortunately, give a value for the optical flux. We'll keep trying. Yeah.
So on that note, let's close here. Let's go outside and carry the discussion on over drinks. And let's join again to thank Vik.
Thank you.
And thank you all.
Thank you very much. Sorry I went on a little bit longer.
Signed up on the I tend to.
I know Nick is going to send.
Yeah, I mean, I'm just going to go. To invest in changing these things.
I thought like he was going to get.
As you see, yeah, thanks for doing it. Really want to get back on the road. I want to get the official route.